Okay, 4.3, we were working with greatest common divisors when we left off. We had talked about two strategies. One that works when things are really small, whoops, there we go, called the intersection of sets method, right? And where we listed things out and we found the biggest number that they both divide by, and that's our GCD. We have the secondary method, which is prime factorization. We talked about that being a little bit more of an advanced idea. It lends itself well for algebra later on, and it's used for larger numbers in general. All right. So I'm going to do another one today called, there we go, division by primes. Division by primes feels very much like that last one that we just did, prime factorization, but it's a little bit more concise. This is, if I were picking, this is probably my favorite one, honestly, because it has some of the features that I really like about the last one, but it simplifies it a little bit. So I kind of like it. So we're going to write all the numbers in a row, and then we're going to divide each of the numbers by a common prime factor. Usually we look for the smallest one if we have it. And then we divide the quotients by a common prime factor, and we keep doing this over and over again until there's no more common factors. And once we do so, the greatest common divisor is the product of the primes. So the thing that it doesn't do, that our last one did, is it doesn't completely factor either of the numbers. But if you're not asked to factor them specifically, that's not a bad thing, because that might end up having been just sort of like overkill. So here's our numbers, 410 and 360. And it says I'm going to write them in a row, so it looks like this. And we're going to do this division algorithm that looks kind of like this one over here on the right-hand side, but we're going to do the two numbers side by side. Okay? So as we take a look at this, we want to find a prime factor, specifically division by prime. So I know these both divide by 10. Y'all see that, right? We're not dividing by 10, though, because 10 is not prime. Okay, are you with me? So we do not have we don't have the same amount of flexibility as we did in, say, like the trees, the factor trees. We really need to divide by a prime. And I generally recommend doing the smallest one possible. What's the smallest thing that will divide both of these? 2, yeah. So we're going to put a 2 out here, and we're going to divide both of them. So 205 and 180. Okay, pretty good so far. I want the next smallest number that will divide both of these. Well, smallest prime. So they don't divide by 2 anymore, right? No. How about 3? No. 18 would, but like 180 would, but the 205 doesn't. So the next one would be 5s. Will 5 divide them both? Yep. What is 205 divided by 5? 41. And how about 180 divided by 5? 36. Now 41 and 36 are already pretty close together, correct? So that's something to sort of be aware of. Man, what number would be dividing both of them? 3 won't work. 3 would work for 36, but it won't work for 41. There isn't one. 41's prime. So the nice thing at this point is that I don't have to keep factoring 36. Like for 36 factors more, right? Yeah, it definitely does. But it doesn't have anything in common with 41, so I don't need to keep going. And the answer is the values right here. So the GCD is 2 times 5, which is 10. Is that all right? I like this one a lot because I feel like you do have to look at both factors at the same time, but I do feel like it gets you to the answer a little quicker than some of the other methods. All right, the most obscure is the next one. Are you ready? All right. The next one is called the Euclidean algorithm, and we're going to write down the steps. They're going to sound kind of confusing as they're written. It's kind of like when we did division by 11, right? It's really confusing sounding, but actually doing it's not that difficult. This is like that. So we're going to divide the larger number by the smaller one. We're probably okay with that step. That makes sense. Big number divide by small number. The second step is to divide the previous divisor by the remainder. Now we've got a lot of vocabulary going on. Divisor by the remainder. Step 3 is to repeat step 2 until we get a remainder of 0. And the last thing that we divided by is the greatest common divisor. Okay, ready to try one? It's really not that hard, so let me show you how it works. So we have two numbers, 72 and 126, and we're always going to divide the big number by the small number. So 126 is going to go underneath your division house, and the larger number is going to go on the outside, 72. All right, so just like when we were doing, like turning things into Mayan and Babylonian and things like that, and we were trying to adjust things, or we were changing bases, stuff like that, we did this thing where we were saying, well, how many times does it go in? And your calculator can help you with that, right? So if you don't necessarily recognize something, or if there's, it's a big enough number that's just not super obvious, you can use your calculator. How many times does 72 go into 126? It's just one time. And then 1 times 72, and we find the difference. So what's 126 minus 72? 54. Okay, so that's step one. All good with step one? Pretty straightforward. What we do next is we take the two values right here, the one we already divided by, and the one that is the remainder at the bottom. Okay? And we put the remainder now on the outside of the division, and we put the divisor underneath. Now, if you've done the first division right, it's going to still mean big number underneath, small number on the outside. Okay, so as long as you're being careful, you can again think that big number on the underneath, smaller number on the outside. How many 54s are in 72? One. And then we subtract. So what is 72 minus 54?
18.
It is 18. We do the same thing again. We take the remainder, we put it on the outside, and we put the divisor underneath. How many 18s are there in 54? It's 3. What's 3 times 18? Remainder of 0, right? The remainder of 0 tells you that we have stopped. It also tells you that the last number that you divided by is your greatest common divisor. So our greatest common divisor is 18, and we're done with the problem. There's not a lot of good intuition for why that should be the answer. Partly why I don't like this method. It feels like there's some trickery going on a little bit, right? But it's not a hard method to do. Okay? All right, we're going to shift gears. We just talked about greatest common divisors. Now we're going to talk about least common multiples. The least common multiple is the least non-zero whole number that is a multiple of all whole numbers in your set. Now, it's really important to think about some grammar here. I'm not an English teacher, but this is a least common multiple. This word least does not mean it's small. It's the least multiple, right? The word least is an adjective for multiple. Multiples are bigger than the number you started with, okay? So if I have the multiples of 5, they start at 5 and then they get bigger, 5, 10, 15, 20. So a multiple is a bigger number, and this is just the smallest bigger number. So if you compare that or contrast that to the greatest common divisor, it's not great. It's a divisor. Divisor means it's smaller, could be the same size, just like this one, but generally smaller than the numbers you were working with. It's the biggest small number. Okay? So jot yourself down and note that in general, least common multiples, well, not in general, very specifically, least common multiples are always bigger or equal than the greatest common divisors. They're always bigger or equal. And the only way that they're equal is if they happen to be the number you're talking about itself. Right? 5 is both a divisor of itself and a multiple of itself. So the answer could be 5 and be both the divisor and the multiple. That's fine. That's rare, but it's possible. Every other time, the least common multiple is bigger than the greatest common divisor. Okay, so we're going to look at, let me see if I have them. I don't. Okay, I'll bring them next time, if I can remember anyway. I'll draw pictures of them. We're going to look at some different models, and the first model actually has a touchy-feely thing with it, right? It's got a kinesthetic learning bit, manipulatives. So it's called color rods. It's also called the number line method. So this method actually shows the multiples of a number on a number line in intervals of each value. What you do is you find the first value at which the intervals coincide. So if you have colored rods, which we do, they're just in my office, I didn't get them here. What this means is that I'm going to have, like, they look like, do you remember when we did the long pieces, the reds and the wood-looking ones? They look like that, so they look like long sticks. And the length of the stick depends on how long, like, what number it represents. So there's like a 1 stick that's like red, and there's like a 2 that's like blue, and there's like a 3 that's like yellow, and a 4 that's green, and a 5 that's, it's how long it is, okay? So different colors for different lengths. Everybody picture what I'm saying? Yes? Okay, good. So what this does, and I'll show you with an example, is it takes numbers like 6 and 15, and it places them in rods, end to end, until they are the same length. And I'll show it to you in terms of a number line, and I'll put my rods in colors on top of them. No, I didn't do it. Thought I changed it black. Let's try again. Here we go. So I'm going to space these out. This is 0. This is 6. So I'm going to use that my 6 rods are red. I don't know what they are in my actual manipulative set, but that's okay. And we have a red rod. It looks like this. And every time I put one down, it's going to be this long. And I just stack them end to end. And so you can see that this one's 6, and then this one's 12, and this one would be 18. I'll do a couple more. And then I have 24, and I have, I'm doing 6 is 36. I missed something, 30. There we go. Goodness gracious. All right, there we go. And I could keep laying these, if I had enough of the manipulatives, right? I could just keep laying them down end to end to end forever, right? This is an indefinite process. But I also have a rod that's supposed to be for 15. So the rod needs to be of length 15 so that I can make it believable. I'm going to start with this. And I'll make them blue. So this rod, the 15, is blue. And I stack those end to end. And what I'm looking for is I'm looking for the ends to coincide. This isn't perfect, but it's not too shabby. If I stack these end to end, the first one goes to 15 with the blue, and the second one goes to 15 more, which would be 30. And this is actually far enough because the ends match. True? What does that tell you? Well, it tells you that the least common multiple is where they match. It's 30. The least common multiple of 15 and 6 is 30. Okay, so that one is the number line model. It's got a really good visual with it. It's got the tactile learning with the manipulatives as well that you can use them with. I don't think that I actually have rods that are 15 long. I think it only goes to 12. So everybody likes the number 12 for some reason in mathematics. And so I think there's a different color for every number up to 10 or 12. But you can still do this same process. You just do it with smaller numbers. Okay? All right, next method, intersection of sets method. So the intersection of sets method is actually very similar to the one I just did. It just doesn't have the picture support for it. So instead, what it does is it lists the numbers out that would have been showing up underneath this number line. So it would actually list out like 6, 12, 18, 24, 30, and 15, 30, 45, 60, and it would list them out. Okay, that's what this method does. So you list all the multiples of each value, and then you find the least value they have in common. So you find the first place they match, just like where the ending lengths matched on the picture. So we have our numbers. They're slightly bigger this time. I have 12 and 15. And what I'm doing is I'm writing down multiples of each of those numbers. So 12 starts with itself, 12, and then it goes to 24. And let's list out like maybe 4 of them. I don't know. We're just going to list out a random number. If it's not enough, we add to it later. We don't want to go too far because if the number ends up being close to the beginning, we would have wasted time. So what's after 24? 36.
48.
16. Okay, let's do one more. 72. And we could keep going forever, right? This is an infinite list of numbers. Okay, we're going to do the same thing with 15, hoping that it doesn't go forever, and it won't. So it starts with 15, and then it gives me 30. What would come after 30? 45. Okay. As soon as we have one in common, which we do at this point already, we can stop our lists. The first number they have in common is the least common multiple. Okay, so this is a really common strategy when kids are in about that 4th to 5th grade age range and they're working with common multiples. This strategy is frequently used. And you'll see lists on their papers, lists of numbers. It's a really good strategy because they've often at this point finally gotten their multiplication facts down, especially with smaller numbers, right? So they can list them out quite adept. They're quite adept at doing so. Even with larger numbers like 15, they've gotten pretty good at this idea of repeated addition or even of multiplication to find those multiplication lists. And so this is a common one that they use. Our next strategy is prime factorization, which looks a lot like the prime factorization for greatest common divisor. The difference is what we do with it at the end. Okay, so the strategy starts out the same way. We find the prime factorization trees or division, bars as we went down. So we're going to construct the prime factorizations. And then when we did greatest common divisor, we listed out the primes they have in common. Here you see on step 2, that's not what we do. We list out all the primes, whether they have them in common or not. Step 3 is that we use the prime's largest exponent. When we did greatest common divisor, we used the smallest exponent. And then step 4 is the same. We find the product of the things that remain. Okay, we get products at the end. So let's take a look at 90, 50, and 20. And I'm going to do my division breakdowns instead of factor trees, but if you like factor trees, feel free to do so. So I'm going to do 90 and I'm going to divide by 2, smallest prime, right? That gives me 45. 45 doesn't divide by 2. Does it divide by 3? Yes, it does. What's 45 divided by 3? 15. Well, 15 divided by 3 again? Yep. And then it gives me a 5. So this prime factorization is 2 times 3 squared times 5. Our next one is 50. What is the smallest prime that 50 will divide by? 2 again. 2 gives me 25. And then what? 5 and 5. So I have a 2 times 5 squared. The last one is 20. 20 divides by 2 again, just like the last ones do, to give me 10, which divides by 2 to give me 5. And this one is 2 squared times 5. Okay, so this is all the prime factors that we have. All right, so take a look then, and I want to list every base that I have as I'm doing my LCM. So what's the smallest factor in any of the factoring expressions? 2. I'll get this exponent in a minute. What's the next in order? 3. And the next? 5. And that's it. Okay? So I list all the prime factors. And then I go back and I look at the list and I list the highest exponent for each. So what is the biggest exponent on the number 2? 2. What is the biggest exponent on the number 3? 2. And what is the biggest exponent on the number 5? 2. Now they're not always going to be all 2s, okay? It just happened to be that this time. I list the biggest exponent and then I go back and I multiply them. So you grab your calculator, you multiply this out, or you can do some of it sort of maybe in your head. This would be 4 times 9 times 25. And that would give me 900. So my LCM is 900. Now, if you wanted to check and make sure that it's at least, it wouldn't necessarily tell you it's the least common multiple, but that it is a common multiple, you could take the 900 and make sure it divides by 90 and 50 and 20. Right? 900 divided by 90, no problem. 900 divided by 50, no problem. And 900 divided by 20, same thing. Yep, Samantha.
So since it's the least common
Mm-mm.
Plus 2 refers to the first 2
Mm-mm.
digits, so what do we do?
No, it's not. No, it's just the largest number that appears.
Okay.
The largest exponent that happens.
But that, like, when you're doing just like regular prime factorization or whatever, you would.
Well, when they're multiplied together, you would.
Yeah.
Like if you had these things that were multiplied together, yes, but we're not actually multiplying these numbers together. We're just comparing them. Right. Okay, so we did prime factorization, and it mirrors the prime factorization from the other one. We're also going to do division by primes, and it's also going to have some sort of similar features as the division by primes before. So you're going to write the numbers in a row. You're going to divide the numbers by a common factor. Okay, so all that part's the same. Step 3 actually talks about dividing all the quotients by a common factor, but it tells you something very interesting that's not true when you do divisors. You're looking for a divisor for any 2 of the numbers. So in the case we're going to do 3 numbers at one time. So if I do 3 numbers at one time and there's a number that divides at least 2 of them, I can still divide it that way. And I'll show you what happens if I don't have it divisible on one of them. Step 4 is to repeat that step until no other common factors can be found. And then step 5 is to multiply the product of the primes. I'm going to change the problem we're going to do just slightly because I'd like for us to just do the last problem that we already did so that you can see the difference in how this works. So the only difference in the problem I had and the problem I'm changing it to is just I'm putting a 50 there, okay, instead of that was the number we had originally. So we're going to write 90, 50, 20. And we're going to divide by the smallest prime they have in common. What is the smallest number that divides them all? 2. Okay, so if 90 divided by 2 would be 45. 50 divided by 2? And 20 divided by 2? 10. Okay, they don't all divide by 2 any longer. How about 3? Nope. 5? Yes. Okay, so we'll divide by 5. Gives me 9 and 5 and 2. Now, this right here, if I stopped, would allow me to find the greatest common divisor. It's 2 times 5. Okay? When I'm finding least common multiple, I keep going, and I look at things they have in common again. So 9 and 5 don't divide by anything in common. Okay? 5 and 2 don't divide by anything in common. And 9 and 2 don't divide by anything in common. Everybody with me? If they did, I would go a step further, and it would look like this. I would say, like let's say for instance, don't change yours, but let me just change mine. Let's say right here it had a 6. Well, 9, 6, and 2 do not have something in common, but 9 and 6 do. 9 and 6 both divide by 3, and I'd write a 3 here on the outside. And I'd say 9 divided by 3 is 3, and 6 divided by 3 is 2, and 2 didn't get divided, so it just gets brought down. That's what we would do. The one that does not divide just gets brought down. Now, I'm going to go back and change it because that didn't actually happen. I don't actually have that. I would have this. There's nothing else that I can divide them all by. So do you know what I do? I multiply these together, including the numbers on the bottom. So my least common multiple is 2 times 5 times 9 times 5 times 2. And it will be the same 900 that I got a moment ago. Okay, there's one more strategy. It's not exactly a strategy, but it's a relationship that exists, like an equation relationship that exists between greatest common divisors and least common multiples. They are not independent of one another. They coincide in a specific way. So this is the GCD LCM formula. It says the following: for any 2 non-zero whole numbers A and B, the greatest common divisor of A and B, that's what the GCD parenthesis AB means, greatest common divisor of AB times the least common multiple of AB is going to equal A times B. And I'm going to use that example that we just saw a moment ago when we had, actually we didn't do one, I take it back, I'll show you the exact example I have. This only works for 2 numbers. I can't do it for 3 numbers. Right? This is a relationship between A and B only, not between 3 numbers like A, B, and C, like the last problem I had. Okay, so it wants you to flip back to problem number 4, example 4 that we did. We had in example number 4, the GCD of, of 72 and 126. What was our GCD on problem 4? It was 18. Okay, so I'm getting that from a previous problem. Let's find the LCM. And we're going to find it using this formula. So this formula says I'm going to take the greatest common divisor, multiply it by the least common multiple. And when I do that, I'm going to get the two numbers multiplied together. Well, that's a 72 and a 126. Those are my numbers. But I know one of them, namely the GCD. The GCD is 18. So if the 18 times the LCM is equal to 27 times 126, how can I find the least common multiple? Yeah, it's like solving for x. So we're going to multiply the 72 and the 126 together. I don't know if I have that written down. I don't. Does anybody have that value? Ty's going to get it for us. 72 times 126. Ooh. 9,072. Like that, Kaylee? Okay, cool. And then what would I do to find the LCM for my last step? Yeah, I divide by 18. Now, it better give me a whole number or I've made a mistake. Okay, so keep that in mind. What'd you get? 504? Like that? Cool. 504 is my least common multiple. Now, could I have found the least common multiple a bunch of different ways than that? Sure, I could. But it's actually a really nice way to find it if I already know the GCD. It's a pretty quick one. Okay. Last couple things is I want to show you a couple examples of word problems and how they look differently for a GCD problem versus an LCM problem. Okay, that's what these last two examples are, is they're word problems for GCDs and LCMs. And this is probably one of those things that you should pay attention to, right? It's an application thing. So think about like the presentation you have coming up next time, right? Not next time, but I mean, we're going to be selecting them next week. This would be an example of the kinds of presentations. Everything I just did in this lesson is not a part of a presentation. Do you realize that? Absolutely had no context until right now. So here's our examples. 2 bike riders ride around a circular path. Can you picture this? Like a track, right? Or like a park. The first rider completes 1 time around in 12 minutes. The second one completes 1 time around in 15 minutes. If they both start at the same place and at the same time, going in the same direction, by the way, all of those are necessary components, otherwise this won't make sense. Right? If they're going different directions, they start at different times, if one of them slows down and the other one speeds up, none of that will work now. These are all conditions that are necessary. After how many minutes will they meet again at the starting place? So will this be a GCD? If it's a GCD, it means it's going to be a number that divides 12 and 15. Or is it going to be an LCM? That is, it's a number that's a multiple of 12 and a multiple of 15. It is an LCM. You're right, Miranda. Do you know why?
Because it just makes sense in my brain. Like, you're trying to figure out how many times until it happens, so the least amount of time until they meet up again.
Yeah, I'm going to take what you said and alter it just slightly. You're trying to find the least amount of minutes, right?
Minutes.
Yeah. So and the reason is that they're going to do this repeatedly. That's a multiple. If they do something over and over and over again, that's a multiple problem. So this is an LCM problem. Now, so finding the LCM of 12 and 15, we can do it lots of ways. Let me do it with division by primes because it's fast. They both divide by 3. That gives me a 4 and a 5 here. And I'm done. 5 and 4 don't have anything in common, so the LCM multiplies these together. LCM is 3 times 4 times 5, and it's 60. 60 what? Minutes. So not 60 times around, right? 60 minutes. After 60 minutes, they will both hit the starting spot at the same time again. Cupcakes. Dr. Hands makes cupcakes for her students. She makes 20 chocolate cupcakes and 24 vanilla. She wants to display them on plates with the same number of cupcakes on each plate, but only one type of cupcake on each plate. What's the greatest number of cupcakes she can put on each plate? Least common multiple or greatest common divisor? Divisor. We're dividing up the cupcakes. Make sense? So when you're looking at these, ask yourself, am I dividing something up or am I doing something a multiple number of times? And that'll tell you which one you're working with. All right? So this is a greatest common divisor. And it's a greatest common divisor of 20 and 24. So let's break them down. I'll do factor trees this time. 20 is 10 and 2. 10 is 2 and 5. 24 is 6 and 4. 6 is 3 and 2 and 2 and 2. So this is 2 squared times 5. And then over here, I have 2 cubed times 3. When I am looking for a greatest common divisor, I need to list only the divisors they have in common, right? Common divisor. 2, right? And I need to list the smallest exponent on the 2, which would be a 2. And 2 squared is 4. 4 what?
4 cupcakes on a plate.
Right, 4 cupcakes on each plate. And I feel like we should have cupcakes.